Hi, I'm David, and I want to talk about our paper, Bit Error Robustness for Energy Efficient DNN Accelerators. In this paper, we show that robustness against bit errors in the deep neural network weights can be helpful to improve energy efficiency of specialized hardware for inference. And this is joint work with Nalini Chandramurthy, Matthias Hein, and Bernd Schiele. Before diving into the details, I will start with a short 2-minute overview. In this paper, we consider the problem of random bit errors that are induced through low voltage operation of DNN accelerators. And these accelerators have become very popular because they reduce cost and energy consumption compared to, for example, GPUs. And because we need to store millions of weights, the main driver of the energy consumption on these accelerators is the memory. So reducing the voltage of the memory can also lead to reduced energy consumption. However, by doing so, we inject bit errors in the memory. And this is illustrated here. The orange curve shows that the energy consumption on the right y-axis is reduced when reducing the supply voltage on the x-axis. At the same time, however, the blue curve shows that we inject exponentially increasing rates of bit errors into the memory as shown on the left y-axis. This means that the DNN has to be robust to exponentially increasing rates of bit errors in order to lower voltage and save energy. On the right, these bit errors are shown to have a direct impact on DNN accuracy. So for example, the orange curve shows the test error of an 8-bit quantized DNN on cipher 10. And the test error after injecting bit errors increases quite significantly, even for small bit error rates. And we consider a robust quantization scheme in brown, weight clipping as regularization in blue, and random bit error training in violet in order to improve robustness, to lower the curve and allow quite significant energy savings. More information can also be found online. Also feel free to come by the poster or just stay for the remainder of the talk. So in the remainder of the talk, I will go into more details. I'll start by briefly discussing kind of the background of how these bit errors originate in DNN accelerators. I'll talk about our bit error models and the contributions, namely a robust fixed point quantization scheme, weight clipping as regularization, and random bit error training. And finally, I'll show that the combination of these approaches can improve robustness and thereby allow to save energy. So DNN accelerators generally feature a large portion of on-chip SRAM, which is used as scratch pads mainly to store the quantized weights of the model. And here data access and movement makes up the largest part of the power consumption of the accelerators. So reducing the supply voltage of the memory is very interesting if we want to reduce the energy consumption further. And as shown here in orange, energy consumption per SRAM access can be reduced when we reduce the supply voltage on the x-axis. Note that both axes are normalized by Vmin, which is the minimum voltage measured for error-free operation. And note that this means that we are already operating at a voltage below the nominal voltage, which is usually recommended by the manufacturer. So while reducing the supply voltage, these SRAM arrays become unreliable. And this is illustrated here for two voltage settings. These maps basically show part of the memory cells. And yellow indicates the probability of a bit flip occurring. And you can see that the rate of these bit errors increases quite significantly when reducing the voltage. And this has direct impact on the stored DNN weights. So in fact, the bit error rate can be shown to increase exponentially, as shown here in blue. Note that the left y-axis is in log scale here. And this means that the DNN has to be robust to exponentially increasing rates of bit errors in order to reduce the voltage and allow energy savings. So unfortunately, this results in significant drops in accuracy. So here we show in orange a normal 8-bit quantized model on cipher 10. Note the change of axes. So we have now on the x-axis the bit error rate in log scale, and on the y-axis the test error after injecting bit errors. And you can see that a robust test error increases quite quickly, even for small bit error rates such as 0.05 or 0.1%. So the goal of our work is to improve the robustness of deep neural networks against such bit errors. The goal, of course, is to allow low voltage operation and improve energy efficiency of accelerators. And to this end, we consider a very simple bit error model, which is still very realistic, namely uniform bit errors across locations and chips. So usually for a fixed chip and a fixed voltage, the bit error pattern can be assumed roughly fixed. But across chips, the locations of the bit errors are assumed random. For a fixed chip, we have further this subset relationship as illustrated here. The bit errors at higher voltage, meaning lower bit error rate, are usually a subset of those at lower voltage. And in practice, we simulate this by sampling 50 different chips with which kind of adhere to this subset relationship. But across these chips, the bit errors are distributed uniformly. So based on this model, we propose a combination of 3 methods to improve robustness of deep neural networks against bit errors. First, a robust fixed point quantization. We combine this with weight clipping as regularization. And finally, we add random bit error training on top. And importantly, and also in contrast to related work, our approach generalizes very well across chips and voltages. And we are able to reduce the energy consumption with only a little increase in test error. So I will start by discussing our quantization scheme. We consider a simple fixed point quantization scheme, which is commonly used in DNN accelerators. Here we use m bits to quantize the weight wi, and quantization is defined by q on the left, where we divide wi by delta, which is kind of the quantization granularity, and then rounding off to the nearest integer. And delta itself is computed by dividing the maximum absolute weight q max by 2 to the power of m minus 1 minus 1. And here we consider a symmetric quantization range. So the weights are between minus q max and q max. And then dequantization takes the integer that we quantized into and multiplies it by delta. And considering the robustness of this quantization scheme against bit errors, the quantization range minus q max obviously is plays a key role. So for example, we can choose it globally across all layers. For example, we can fix it to 1. And then we show on the left plot on the x-axis the original weights, and on the y-axis the weights after bit errors with bit error rate 1%. And yellow points indicate kind of a larger error. And in practice, however, usually people do a per layer quantization. So the quantization range is adapted for each layer. And you can see in the middle that this already reduces the impact of bit errors. And we additionally also allow asymmetric quantization range, which further limits the impact of bit errors on the right. And this works particularly well for layers with kind of an asymmetric quantization range, an asymmetric weight distribution. So for example, biases or normalization parameters. So the impact of these changes is summarized here in this table. Note that the clean test error in the first column remains nearly unchanged. So this means that we are talking about details in the quantization that usually do not matter in terms of clean accuracy, but may become very important in terms of robustness. So when injecting bit errors of rate 0.5%, you can see that compared to the per layer symmetric quantization, asymmetric quantization actually at first increases the robust test error. However, this is because we quantize into signed integers. As soon as we quantize into unsigned integers, which is the third column, we can reduce robust test error from 24 to 17%. And then replacing the floor operation by proper rounding, we can further reduce that to 11%. So overall, this table illustrates that there might be a lot of quantization details that have been overlooked previously, but they become very important when we talk about robustness. And I want to make the point that this becomes more and more important for low precision models. So here for 4-bit quantization, implementation details such as proper rounding make the difference between a random classifier, so 90% robust test error, and a decent performing one. Note that these results are already with weight clipping, which I will talk about next. So overall, proper robust fixed point quantization can reduce the robust test error, as shown here in brown. However, for medium to large bit error rates, the robust test error still increases quite significantly. So we still need to tackle that. So next, we consider weight clipping as a regularization, which we combine. So this is on top of robust fixed point quantization. Weight clipping essentially limits the weights to the interval minus W max during training, for example, just by clipping the weights after each update. And note here that W max also limits the quantization range, but we can still have a quantization range smaller than W max for each layer independently. So one could think that weight clipping trivially reduces the impact of bit errors by bounding the quantization range. However, in practice, this is irrelevant because we don't care about the absolute errors, but we care about the relative errors. And in fact, as shown here, weight clipping actually tends to increase the impact, so the relative impact of bit errors. So this is shown here with our robust fixed point quantization scheme without and with weight clipping, and you can see on the right that the impact in terms of relative errors of weight clipping is increased, highlighted in yellow here. So the impact of weight clippings on the deep neural network predictions is illustrated here. On the right, you can see the impact on the weight distribution. So on the lower right corner, you can see that we indeed clip the weights to minus 0.1, 0.1. Nevertheless, the DNN is able to achieve nearly as large logits as the original network, as shown on the left. And more interestingly, the logit distribution is nearly preserved when injecting bit errors, which is kind of the red distribution shown. And as a result, the confidence is preserved better as well. And this is shown in the middle, where I also highlight the average confidence on clean, so clue, and perturbed weights in red. And this is in stark contrast to the reference model. So preserving the logit distribution directly translates to better robustness. This is shown here for a bit error rate of 1%. We reduce the robust test error from 32% to 13%. And one question is, of course, why does weight clipping work that well? And we suspect that limiting the weights while at the same time minimizing cross-entropy loss is the key. Because minimizing cross-entropy loss needs that we want to have large logits. But in order to obtain large logits, we now need to utilize more weights because each individual weight is limited. So we induce kind of some sort of redundancy in the weights. And to test this hypothesis, we trained a model with label smoothing. Label smoothing essentially takes away the need for large logits. And you can see as soon as we do that, the robust test error increases again, as highlighted in red. So overall weight clipping shown here in blue, it's very simple to apply and improves robust test error quite significantly. So now for even larger bit error rates, we are below 8% test error. And of course, it's important to note that this is on top of robust fixed-point quantization. On top of these approaches, we also employ random bit error training. Here we quantize the weights during training as with quantization aware training. However, we additionally inject bit errors in the quantized weights before dequantizing them. And then we compute the gradient, meaning forward and backward path on both the clean and the perturbed weights. And then we perform an update based on the average of both gradients. And it is important here to train on completely random bit errors. A related work, for example, often uses profile bit errors for one specific chip. And the disadvantage of that is shown in this table. Here we train a model on a fixed bit error pattern, for example, for 2.5% bit error rate. Note that the pattern of the bit errors is fixed, but we still have some randomness within the pattern. And interestingly, this model does not generalize to lower bit error rates as shown in red. So for lower bit error rates, the robust test error actually increases. So we don't generalize to higher voltages, which is unintuitive. Similarly, these models also don't generalize to completely random bit errors, as shown on the bottom. So if we train on fixed bit error patterns, so on profile bit errors for a specific chip, we neither generalize across voltages nor across chips, but we overfit to the bit error pattern that we trained on. So random bit error training further improves the robustness. So this is again on completely random bit errors, as shown in the violet line here. And we can now show that this actually leads to quite significant energy savings. So for example, we can save 20% of energy just by a increase of 1% in a test error. And of course, higher energy savings are possible with a higher increase in test error. This also works for lower precision. So here we have a 4-bit model, which is shown using the dashed black line. You can see that there is only a slight increase in test error compared to the 8-bit model in the solid black line. And the advantage of doing this with low precision is that we combine the energy savings from requiring less memory with low voltage operation of this memory. Finally, I want to show that our approach also generalizes to profile bit errors. Here we have 2 chips. The first chip is very close to our uniform bit error model. Here we generalize very well. Even for very large bit error rates of 2.75%, we still have reasonable performance. Chip 2, in contrast, has a slightly different distribution as shown above. The bit errors are aligned strongly along columns, which deviates obviously from our uniform bit error model. Still, we generalize to lower bit error rates in this case. With our random bit error training. In conclusion, we consider a uniform bit error model that realistically captures the nature of low voltage induced bit errors across voltages and chips. We propose a robust fixed point quantization scheme combined with weight clipping as regularization and random bit error training to improve robustness. And in our paper, which you can find online, we also have results on MNIST, Cypher 100, and also discuss guarantees. Finally, I want to highlight some follow-up work that we recently released on arXiv. Here we further improve robustness using per layer weight clipping. So the improvement using the dashed line is shown below and is quite significant. We also consider bit errors in inputs and activations because those are also temporarily stored on the SRAM and are subject to low voltage induced bit errors. And finally, we also consider adversarial bit errors and ask whether we can get robustness against bit errors maliciously flipped by an attacker, for example, through a row hammer attack. So thanks for your attention. Make sure to check out the poster session or the paper online.